In this video, we are going to study how to construct a confidence interval for a population mean. Now let's consider a problem. We would like to estimate the mean GPA of the US senior high school students using our class data, assuming that it is a representative random sample. Moreover, we wish to determine the margin of error for our estimate to have a measure of its precision. So the goal in this section is to use a sample mean, which is our class, to make inference about the value of the population mean. So the problem here is that how do we know that our sample of the class, our data of the class is good enough to represent the whole US senior high school students? And in this section, we'll try to construct the confidence interval to make that prediction. Now there are two parts for the estimating a population mean. The first part is when we do not know anything about the standard deviation sigma of the whole population. So part 1 is estimating a population mean when the standard deviation sigma is not known or given. And then in the next video, we'll see how we estimate a population mean when the standard deviation sigma is given. We use something called a student T distribution when the population standard deviation sigma is not known and the sample size is small. Remember, from the other video, we use the standard normal distribution for estimating a population proportion, but for the population mean, we use the student T distribution when the standard deviation sigma is not given for you, and also the sample size is small when n is less than 30. However, if the standard deviation is given is known, then we use the normal distribution instead of the student's T. So let's take a look at the characteristic of the student T. Now, there's a few notation. We use the mu notation to represent the population mean, the x with the little bar to represent the sample mean, and then it is number of the samples values taken from a population the population, and E is the margin of error, and then the small letter s is a sample standard deviation. If a population has a normal distribution, then the sample jar also has a distribution of the student T distribution with the degree of freedom n-1. So make sure that your population is normal. Then the sample that is drawn from that normal distribution of the population will have a distribution of the student T with the degree of freedom n-1. And this is the formula for the T distribution. The x bar minus the mu over s is the sample standard deviation over the square root of n. Now, if the original population is not itself normally distributed, we use the condition n needs to be bigger than 30 for just justifying the use of the normal distribution. If n is less than 30, make sure that the original population is normally distributed. If n is bigger than 30, then it's okay to have the original population that is not normally distributed. So we can think of the T distribution as the Z distribution but with an adjusted standard deviation that increases for smaller sample sizes to account for a larger margin of error. And then the degree of freedom, df equal n minus 1. This is the number of the values in the final calculation of a statistic that are free to vary. So for instance, if there are 10 test scores that have the restriction that their mean is 80, then the sum must be 80. And we can freely assign the values to the first 9 scores. But then the 10th score would then be determined to make sure that the sum need to be 800. And therefore, we always have one less than the total number of the sample size for the number of the degree of freedom. And the critical value T alpha over 2 can be found by using the technology TI-83 or 84, or we can use the table, the distribution table from the appendix. Okay, let's go over one equation, one example. A sample size of n equal 12 is a simple random sample selected from a normally distributed population. Find the critical value T alpha over 2 corresponding to a 95% confidence level. And the answer is n equal 12. 12 is the sample size, and therefore the degree of freedom n minus 1 or 12 minus 1 is 11. The next step, we are looking for 95% confidence level, 95% confidence level. And when there are 95% confidence level, then your alpha is the order 5%, which is 0.05. And alpha over 2, because we need alpha over 2, so alpha over 2 is 0.025. And we know that this is the area to the right of the distribution. So this is the t distribution. The center is when t equals 0, t alpha over 2, and because this is symmetric, there's also minus t alpha over 2. So 0.025, this is the area of alpha over 2 to the right of alpha over 2. Okay? And therefore, we know that everything has the area of 1. We take 1, we subtract this portion, we will get this area, or 1 minus 0.025 for the remaining of the left side. And now, once you have the area up from the left side, you can use the inverse t function from TI-84 to find the t of alpha over 2. So let's try that here. Okay. Second, distribution, go to inverse t. This is inverse t. T is t distribution. The area, this is always the area to the left of this value that you are looking for, 1 minus 0.025. Degree of freedom, we have 11. And that should give me 2.201. Okay. And this is just the command that I just showed you. INV inverse t, area to the left, degree of freedom. And that is how you find the t alpha over 2. Or you can find that using the t-distribution table, and we are looking for the area of the right. So if you are using this table, we take the area of the right of that value 0.025, one tail, which is right here, and we are at 11 degree of freedom, and that should give me 2.201, which is the same thing. Now, how to construct the confidence interval for the mean? Again, we have two important requirements. The sample is a simple random sample. Either or both of these conditions is satisfied. The population is normally distributed, or the sample size is needed to be bigger than 30. Then the confidence interval, we take the sample mean minus the margin of error to be the lower bound, and then plus the margin of error to be the upper bound. And we use the same notation that I discussed earlier. Population mean for mu x bar sample mean is margin of error as sample standard deviation, and is the number of the sample. And therefore, you can find the lower bound x bar minus t alpha over 2 times s over the square root of n, and then change the minus to the plus for the upper bound. And there's a note here: as the level of the confidence increases, the margin of error increases and the interval becomes bigger. As the sample size increases, the margin of error decreases and the interval becomes smaller. So please keep that in mind. Okay, constructing a confidence interval for the highway speed. The data below lists the speed mile per hour measured from the southbound traffic on the I-280 near Cupertino, California. This simple random sample was obtained at 3:30 p.m. on a weekday. The speed limit for this road is 65 miles per hour. Now use the sample data to construct a 95% confidence interval for the mean speed. And what does the confidence interval suggest about the speed limit? So this is the given data. This is the measurement that we have for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cars. This is a simple random sample was obtained from 3:30 p.m. on a weekday. So this car has a speed of 62 miles per hour. This guy has 59, and this guy has 67, and so on. Now, as the first step, we always do the requirement check. That is the first step. Okay, requirement check. This one is a simple random sample, so that is good. Remember, we have two requirements. The sample is a simple random sample, and then we need the population to be normally distributed, or the sample size to be bigger than 30. So this one is already a simple random sample, and we can use the dot plot to verify that the speeds have a distribution that is not dramatically different from a normal distribution. Now, because this one's right here, we only have 12 data points, so n is less than 30, so we need the population to be normally distributed. Or you can use the dot plot to verify that the speeds have a distribution that is not dramatically different from a normal distribution. So after we do the verification, we can then calculate X bar. This is the sample mean. So how do I find the mean of this value? I add all of them and I divide by 12. Standard deviation. Actually, I can use the TI-84 to find sample mean and standard deviation to be these two values. And from T of alpha over 2, remember this value we got from the lattice sample. The lattice sample, because we are also constructing a 95% confidence interval. And for 95% confidence interval, with the 12 data points, then T alpha over 2 we got earlier 2.2. So from the lattice sample, we got this value, and therefore we can use the lower bound formula. We have everything, and then we 1 is minus, 1 is plus to get the lower and the upper bound. And we can make a conclusion. It appears that the mean speed is below the speed limit because 63.3 is below 65 miles per hour. Okay, so now let's see how I found these two values. Okay, let's do that using the TI-84. Okay, so first thing you're gonna go to edit, start, edit. Now you want to enter the value of the data into the list here to store the data. 61, 57, 61, 54, 59, 58, 59, 69, 60, 67. And then now you're gonna go back to quit, go to start, go to calculate. Okay, and then you're gonna hit one variable statistic. The list is the list L1. We just store the data into list L1. And you're gonna go to calculate, and then it gives you all the statistics of list L1. So we got what? The X bar, the mean. Okay, standard deviation S is SX right here for 4.1. So this one is the sample standard deviation. And then N12 and so on. So that's how we use the TI-84 to help us to find that. You don't have to do this by hand. Now before we move on this problem, let's go back to the beginning of this problem for the requirement check. Because we only have 12 value n equal 12, so n equal 12 is less than 30. It's less than 30, and therefore we need to make sure that the population is normally distributed. So how do we do that? Well, there's a few ways you can use the dot plot to check, but there's an easier way on the TI-84 that you can do. So let me show you here. First thing, again, this is our data point. We're gonna list them in the list L1. Okay, so make sure it's in the list L1. And now you're gonna use the start plot. So second start plot, we are going to use plot number 1 So I press enter, I turn it on, and then I want to draw the normal probability plot, which is the last one. So move to the last one, hit enter, and then this is the normal probability plot. And then the data list is L1. The data axis is your x-axis. And then you can choose any marks. And that's all. Okay, so you're gonna quit. Go to zoom and choose the option 9, zoom start. Now, if you plot the normal probability plot and there is the pattern of the linear line, a straight line, then it confirms that the sample that we have here is coming from a population that is normally distributed. So if you get something like this one here, this is good. This look like a linear, right? This is a linear pattern. Yeah, this is a linear pattern. You can think of the linear pattern something like this, where you can have a linear line that goes through all the point. And if you get something like this sample here, then in this case, there's no way you can draw the linear line. This is not a linear pattern. This is a linear pattern, but this one is not. So if you do get a linear pattern for the normal probability plot, then your sample does come from a population that is normally distributed. That's why the requirement check here is okay. The next objective is to finding a point estimate and the margin of error from a confidence interval. So similar to the section of the population proportion, we can also find the margin of error and the sample mean or the point estimate by using the upper and the lower confidence interval. So for example, the margin of error is found by getting the upper confidence interval limit, subtract the lower, and then divide by 2. And then for the sample mean, we add them and divide by 2. Now, the last objective for this video is to determining the sample size. How many sample units n must be obtained? So the question is, how many units? What should be the sample size that we should obtain for a particular research or projects? Well, there's two cases. When the standard population of the population sigma is given, we can use the z statistic, not t statistic, to find the sample the sample size n by getting the z-score of alpha over 2, the critical value, multiplied by the sigma or the population standard standard deviation, and then divide by the margin of error, the whole thing square, and that should give you the sample size. And remember, if the sigma, the population standard deviation, is given, we use the z statistic, not the t. So z alpha over 2, not t alpha over 2. But usually sigma is not given or unknown, then we can use the range rule of thumb. Sigma is equal to the range divided by 4. Or we can use the first several values of the sample to calculate the sample standard deviation S, and then we use that in the place of sigma. And therefore, the formula becomes n equal z alpha over 2, the small s, this small s is sample standard deviation over E, the whole quantity square. So, two cases. If it's given, then it's very easy. We use this formula right away. If sigma, the population standard, is not given, you have two choices. You can use the rule of thumb, the range divided by 4, or you can use the first several values of the sample to find the sample standard deviation s, and we treat this small s as a sigma value. Alright, so let's go over the for the sample for this objective. Assume that we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for the IQ test of if we want 95% confident that the sample mean is within 3 IQ points of the population means, and we assume that the sample standard deviation s is 15. So in this case, we want to know how many statistics students must be randomly selected, or we are looking for what is the sample size n, right? And because we want the sample mean to be within 3 IQ points of the mean, therefore the margin of error E is equal to 3. Within 3 IQ points of the population mean is the same thing as we want the margin of error E to be 3. And because we are given the assumption of the small letter s, the sample standard deviation equal 15, therefore I use this formula right here to find the sample size n. The s is 15, E is 3. Now z alpha over 2 is 1.96. Now, how do I find that? Well, because in this case, let's quickly find what is z alpha over 2. Now we know that the problem wants 95% confident interval. Therefore, the alpha is the order 5% or 0.05. Remember, alpha is the complement of the confidence level. Together, they add up to be 100%. 0.05. And therefore, we are looking for alpha over 2, 0.05 divided by 2, 0.025. Okay? And then we can draw the normal curve, like this one here, the normal curve. And z alpha over 2 is right here. The standard normal distribution, they have z alpha over 2 over here and minus z alpha over 2 over here because they are symmetric. And we know that the alpha over 2, 0.025, this subscript right here, it means that the area to the right of that is 0.025. Now to find the area of the rest over here, we get 1 subtract to the area to the right, 0.025. And if I do that, I get 1 minus 0.025 or 0.975 for the left area of this value. And we can then use the inverse function from TI-84 to help you to find that z's value. So what we do now, we go second distribution, we go to inverse norm. This is the normal distribution curve, so we are looking for inverse. Remember, the inverse function is used when we know the value of the area, and we would like to know that x value. The area is always the area to the left of that point. We are looking for this point, and that area to the left is 0.975. 0.975. And then the mean, again, this is the z scale. So the mean should be 0. And the standard deviation is 1. And we paste everything into the function of inverse norm, and that should give me 1.96. That's why I got 1.96 for z alpha over 2. This point right here is 1.96, which is what I got over here. And then again, as a rule, we always round up the number, so to the next whole value. So 96.04 is equal to 97. That is the whole, the next whole value, the next integers. So 96.04 is 97. So we need to have the sample of 97 statistics students to be randomly selected for the IQ test.